I will start to begin. I'm very happy to have Andy Neitzke from Yale tell us about abelianization of the Virasoro conformal blocks.
Great. So thanks very much for the invitation. It's always a pleasure to visit Berkeley. So I'm here, unfortunately, only for one day, but so I hope to meet as many of you as I can. Right, so I'm going to talk about abelianization of Virasoro, and I have to say Virasoro at c equals 1, so far, conformal blocks. And this is a report of work in progress with Qianyu Hao. So, the details are still getting in place, but by now the basic picture is pretty clear. And it's motivated by work of many other people. So in particular, we kind of got started when we were thinking about the work on non-perturbative topological strings of Coman-Longhi-Pomoni-Teschner, and some closely related papers of Iwaki, Iwaki, a paper of Iwaki with Marino, work on free fermions by Gavrilenko and Marshakov, and Tom Bridgeland on tau functions. Okay. So my talk will be independent of these previous works, but I want to say it's motivated by things that those people have been thinking about. Okay, so this is going to be a story about conformal blocks, so I should first tell you what is a conformal block. So what is a conformal block? And maybe different people have slightly different definitions, so I want to be sure what I mean by conformal block. So we're going to talk about conformal blocks, two different flavors of conformal blocks. So the simpler ones are the Heisenberg blocks, so let's start with that. And so let's fix a Riemann surface. Say C. It'll usually be compact. The definition, it doesn't have to be compact or anything. So a Heisenberg block psi, or let's say a Heisenberg block on C, I'll call it psi, is a bunch of numbers. Sometimes we would call those numbers correlation functions or chiral correlation functions, chiral correlators. So the notation is like this. I put these angle brackets and then I write in them, I write j of p1 up to j of pn. So it's going to be a number depending on the data of n points of the Riemann surface, p1 up to pn. So maybe p1 is here, p2 is here, up to pn. So those numbers I denote by this symbol. I put a psi here to say these are the numbers associated to the conformal block psi. Except actually there's a detail, they don't depend just on the points, they also depend on around each point I have to choose a local coordinate system. So around this point maybe I have a local coordinate z1. Around this point I have a local coordinate z2 and so on. And so when I'm being careful I'll write that dependence also. So given that data, a bunch of points with little coordinate chart around each point, then I'm supposed to get literally a number. And of course, they should obey a bunch of properties. So first of all, they should depend holomorphically on the points. Holomorphic in the points pi, p1 up to pn. So psi is the name of this collection of numbers. So I'm going to define for you what's a conformal block. And a conformal block is going to be a whole bunch of numbers.
So psi is the name of the conformal block.
That's right, that's right. That's right. I put this little subscript here just to keep track of, these are the numbers that come from that conformal block. So they should be holomorphic as long as we're away from the diagonal, so as long as no 2 points collide. Then when the points do collide, they're supposed to obey a relation. I'm going to write the relation in a slightly symbolic way. I'll write the relation like this, that J of P, J of Q, if now P and Q, suppose they're both contained in a common coordinate disk. When P and Q come together, they're supposed to have a singularity which looks like this. It's supposed to be 1 over the z coordinate of P minus the z coordinate of Q squared plus regular. Now, what does this mean? What I really mean is that this relation should hold inside the correlation function. So for example, these are z's. Yeah, sorry about that. All of these are z's, not 2's. Yeah. No, this whole thing is a number. And now I'm going to explain what I mean by this kind of symbolic relation that these numbers. The subscript psi is just part of the notation keeping track of. So the conformal block is a collection of these numbers obeying some relations. And that collection, to keep track of which collection I'm studying, I put a little psi. So let me explain what I mean by this relation. So for example, if I look at the 3-point function, J of P, J of Q, J of R, and so it's supposed to be holomorphic away from P equals Q. And the question is, what happens as P approaches Q? And what happens is that I get a pole. This J of P and this J of Q get replaced by a second order pole, Z of P minus Z of Q squared. And then that's multiplied by the correlation function of the remaining thing. So here it's just J of R. So in general, what this says is that if I look at the n-point function, by n-point function I mean the one with n insertions here, its poles along the diagonal are controlled by the n minus 2-point function. To see the pole as P approaches Q, I just replace this by this up to regular. So here, this is in plus regular terms. As P approaches Q. So okay, that's, so I'm listing the properties of these of conformal blocks. These are 2 properties that they're supposed to have.
So say you have some meromorphic function on symmetric products on the surface.
Right, except it's not, I said it also depends on these local coordinate systems. So for that reason, it won't be quite just a function on the symmetric product. But I'll say in a second.
When you say in C, sometimes.
Oh, yeah, it's in C as long as the P's are distinct. As long as the P's are distinct, it's really in C. Yeah, thanks. I may as well say it's defined only when the P's are distinct, and then it's literally in C. Okay, good. So so as you just mentioned, they should be symmetric in the PI. So the order that I write these symbols doesn't matter. And the last thing is I told you that they depend on the local coordinate system, but they depend actually in a very controlled way. The dependence on the local coordinate is just this. If I write the thing in local coordinate W, it differs from the thing in local coordinate Z by a factor of dz dw, evaluated at the point P. I may as well write it like this, dz of P divided by dw of P. So I said it depends on the local coordinate system, but in fact, it just depends on the first derivative. Right, so another way you could say, right, for these particular conformal blocks, another thing you could say, indeed, is that it's a global object which is a kind of poly-differential. It's like a one form in each. It's a one form in each variable, defined on the symmetric product, with poles of this particular kind. Indeed. Okay, so that's the definition. So that's what I mean by a Heisenberg conformal block. It's a bunch of one forms on the symmetric product with these kind of poles. Okay. So what can we say about these Heisenberg blocks? Well, they form a vector space. I'll call that vector space conf of C comma highs. So by highs, for people who've thought about vertex algebras, you'll recognize that this J is to be thought of as the generator of the Heisenberg vertex algebra. Means the Heisenberg vertex algebra. But for what I'm going to say, you actually don't need to know about vertex algebras. You can just take this to be literally the definition of conformal block. Right. So I'm trying not to say what kind of objects they are. I'm just saying that I'm introducing a bunch of functions, and I have a rather complicated notation for the function. The function of P1 up to Pn, I write by this notation, this angle bracket, J of P1 up to J of Pn. Under pressure, you could say that this J is kind of the fundamental field generating some vertex algebra. But I would rather just focus on the functions.
But then when you say something about the product.
Right. So that equation there, right. So this is the kind of slogan that tells you how the n-point function is related to the n-2 point function. So this you can take as just kind of a macro. Here's the sort of concrete example of how you use it. So this tells you how the 3-point function is related to the 1-point function. But of course, encapsulating it like this is very convenient. But what it means really is this relation on the functions, nothing else. Okay. Good. Okay, I'll come to that in a second. So before saying that, let's say, why is it a vector space at all? It's a vector space just because all the conditions are linear conditions. So if I have a conformal block, I want to define the sum of two conformal blocks. By definition, the correlation functions for the sum of those two conformal blocks is just the correlation functions for the first one plus the correlation functions for the second one, where I put the same combination of j's in all three places. I guess to say it's really a vector space, I should put alpha here and beta here, and so that it's alpha times this and beta times that. So they form a vector space just for that reason. And so we can ask, indeed, we can ask, okay, now it's a mathematical question. Given a Riemann surface, what is that vector space? What is the space of all conformal blocks? No. This psi appears everywhere. So yeah, very good. So I should have written. So it is homogeneous, right? If I multiply it by alpha, this side also gets multiplied by alpha. Right. The point is, one single symbol psi captures the whole system of correlation functions.
So you could have, say, just the two vectors in there.
That's right. Another relation I could have written is, yeah, very good. Very good, yeah. We didn't talk about, so I said it's a collection of numbers where n starts from 0. And so the 0-point function, I could write it like this. And that's some number which depends linearly on the block. We often write notation like this. We put a 1 there. It does not have to be 1. Absolutely not. No, that's right. That's very important. Yeah. Good. Okay, so the Heisenberg blocks form a vector space, and so we can ask, what is that vector space? Okay, so the simplest thing we could ask is, how about take C to be just CP1? Okay. Oh, I see. I haven't done this well. All right, so I have to start erasing. So, so in the case of CP1, the space of conformal blocks, of Heisenberg conformal blocks, is one-dimensional. You asked, is it finite dimensional? For CP1, the answer is it's finite dimensional. In fact, it's one-dimensional. So let me tell you concretely what the conformal block is. Well, okay, so it's spanned, the space of conformal blocks is spanned by a single psi. And so to specify what psi is, I'll fix the 0-point function to be 1. So once I specify that, I've uniquely specified the block. And now the rest, okay, so the 1-point function of J, in this case, is just 0. The 2-point function, here I may as well use the global inhomogeneous coordinate, the inhomogeneous coordinate on CP1. In fact, well, yeah, I'll write it like this. So 1 over z of p, it literally is just 1 over the difference of the point squared. Sure enough, you checked it satisfies this condition, and so on. So you can determine iteratively all the higher ones. They're all uniquely determined. Okay. So on CP1, this notion of conformal block is maybe not too interesting. Now you ask, what about a higher genus surface? Okay.
So maybe a very naive question.
Yeah.
Suppose
Yeah.
pretend it's like a sandwich between two vacuum states.
Yeah.
But this should be a bilinear form in the.
Yeah. In this case.
Why this linear side?
Well, psi is just my definition of. Yeah, it's like you're rescaling kind of one of the vacua, if you like. I mean, yeah. But anyway, right? Sure enough, these are the things you would compute if you did the usual kind of CFT computations of 0, j of z, j of w, 0, and expanded in modes, and so on. It'll produce for you this answer. So far there's nothing new. Okay, so how about genus greater than 0? Well then, this space is infinite dimensional. So in this talk, we basically will not discuss any finite dimensional vector spaces. They'll all be either one-dimensional or infinite dimensional. Why is it 0? Because the constraints that I told you imply that it should be a global holomorphic one form on the surface. And on CP1, there's no global holomorphic one form except for 0. So that's why that one has to be 0.
The second one would be a holomorphic one form on CP2 with poles. The second one would fall on the quadrant, right?
Yeah.
So that's like a section of O of 1. So why is there only one such thing and not 3 such things?
Well, I didn't say that there's. Let's see. You were a little too fast for me. So I think the statement is that if I subtract this one, so suppose I subtract this one, then I'm going to have a holomorphic bi-differential on CP1. And the question is, why are there none of those? I think. I mean, if you held, okay, subtract them and then hold Q fixed and just look at it as a function of P, then for the same reason as before, it has to be 0. Okay, I'll take that as that you're convinced. Okay. Now we go to the higher genus case. And in higher genus, this space of Heisenberg conformal blocks is infinite dimensional. And let's think a little bit about how we might organize it. So it's infinite dimensional, but nevertheless, we can more or less, we can understand it very well. And the reason is that we can realize it as a representation of a rather simple algebra. So it's acted on by operators. I'll call the operator L gamma, where gamma is a homology class on my surface. So for every loop on the surface, I'm going to give you an operator on the space of conformal blocks, on this linear space of conformal blocks. And what that operator is, so given a conformal block, I'm going to make a new conformal block, L gamma psi. So I got to write the correlation functions of this one in terms of the correlation functions of the original psi. And what it is, so whatever combination of j's, I'll put the same combination of j's here, but then I'll put one more thing. I'll put the integral around gamma of j of p z dz. Maybe you ask me what I mean by putting this integral. So I mean that everything is supposed to be linear. So what I really mean is this. So I just insert, to make my new conformal block out of the old one, I insert one more operator, j, and I integrate it around a loop. Now you might worry about this. You might worry that after I've inserted this contour integral, the correlation functions will have new singularities that they're not supposed to have, right? Because if I insert some j here, right, the correlation function with that j inserted, it's supposed to have no singularities. On the other hand, it looks like it's in danger of having a singularity when my insertion approaches the contour. But the point is that because in this operator product, there's no residue, the residue at the singularity is 0, so you can safely deform the contour across the insertion. And so you really get a well-defined answer for the correlation functions, even the ones where j is inserted exactly on this loop. Okay, so I just told you the definition of a bunch of operators, a bunch of linear operators acting on this space of conformal blocks. Now, there's an interesting computation you can do, which I won't do in real time. Right, okay, good. That's exactly the question. Do they commute? That's the thing which I'm going to tell you the answer, but I'm not going to, okay, unless someone asks me later, I'm not going to do the calculation. But let me tell you the answer. So the answer is they don't commute, and that's what makes it interesting. So what it turns out is that the operator associated to a loop L and the operator, the operator associated to gamma and the operator associated to gamma prime, they fail to commute by the intersection number of gamma and gamma prime. Maybe it's not too surprising if they're disjoint loops, then they commute. But you can see there's some potential issue when the loops intersect. Everything is still well-defined. These are well-defined operators. Their commutator is some definite thing, and when you carefully calculate it, it comes out to be this. Okay, so we have this non-commutative algebra, but a very simple non-commutative algebra, kind of Heisenberg type algebra acting on this space of conformal blocks. And so now we might try to study this space as a representation of this algebra. Well, because of this, it's hopeless to try to build conformal blocks which diagonalize all of the operators. We could try to diagonalize half of them.
Suppose you want to compute the infinite function of L gamma prime acting on psi.
Yes.
What expression would you like to have?
Well, it's a little tricky, right? So yeah, so very good. So yeah. So what is the correlation function with L gamma prime acting on psi, right? So by definition, that's the correlation function. This dots just means some insertions of j's, where I take an integral over gamma of j in the block L gamma prime of psi, right? Now you try to compute, when you write the next thing, you get a little confused because you say, oh, there's going to be a moment when the two j's, when these two contours intersect. It looks like it has a singularity. But the definition of this tells you what to do, right? The definition of this was that I insert the integral of j along the contour gamma, but then if necessary, I can deform the contour a little bit to either side. Right? When I told you the definition of this, I allowed the possibility of deforming the contour a little bit to avoid a singularity. And so what you wind up doing ultimately is integrals like this. You have to do these kinds of things. And you compare it to, so this is if you do them in one order. If you do them in the other order, then you have something like this. Okay, now I got to draw the thing this way. Minus that one, minus that one. So this commutator involves considering four things where I do contour integrals in this kind of way. And in the end, they don't quite cancel each other, and so I get this. Okay, but it's some definite computation that you can do. Okay. Okay, so we have this non-commutative algebra, and now we want to think about this space of Heisenberg blocks as a representation of that algebra. Because it's non-commutative, we don't hope to diagonalize all of them, but we could hope to diagonalize half of them. So suppose we choose a basis of A and B cycles. A1 up to AG, B1 up to BG on C, where the intersection pairing is the usual thing. I guess people call it a symplectic marking. So because the A cycles have zero intersection, we could try to diagonalize all the operators associated to the A cycles. And sure enough, then we can explicitly construct them. So then we have elements, all right, psi x in conf of, in the space of conformal blocks, which have these AI operators are diagonalized with eigenvalue, sorry, this is x is x1 up to xg in c to the g. So you fix the kind of joint eigenvalue of the A cycle operators. And then sure enough, you can diagonalize those operators. And then the B cycle operators act as derivative, 2 pi I derivative with respect to x. So in other words, you're constructing kind of the usual Schrodinger representation of this algebra, where A acts as x and B acts as d by dx. That's right, that's right. All this is, so I'm saying in that case, what we see essentially is like the quantization of the first homology. The fancy way of saying it would be that what we're producing here is kind of the quantization of the first homology of the, that's a good way of thinking of this space of conformal blocks for Heisenberg. Okay, so that's a relatively simple and concrete thing. If I want to construct these psi x explicitly, we would get a little into technology of compact Riemann surfaces. We would have to use the, what's it called, the Bergman kernel and that kind of stuff. But it's somehow all well-known stuff that just involves theta functions. So morally, what I'm saying is that we can understand conformal blocks for Heisenberg completely if we understand a little bit about theta functions.
Are you saying that this is an irreducible representation?
Very good, very good. So yeah. So what I would like to say, is that these elements form, in some appropriate sense, a basis for this space. Of course, it's a little, so people talk about a basis in the space of conformal blocks. Okay, I don't have a rigorous statement to make about that, but certainly informally, that's how we think of it, is that these psi x kind of span all conformal blocks.
Like I said, the
Oh yeah, unique. Yeah. There's these conditions uniquely determine those elements. Yeah, uniquely up to one overall scale, one overall normalization. Yeah. And indeed, I want to say that sort of every conformal block that we'll ever care about, you should think of them as being some linear combinations of these elements. Okay.
Question. Is the LBI acting on psi x that relation? Does it follow from the first relation?
No, it doesn't follow from the first relation. It almost follows from the first relation, but this one is insensitive to the normalization of psi x, whereas this one is not. So essentially, this one, you would think that this relation determines psi x up to a function depending on x, up to multiplication by a function depending on x. This one fixes the freedom of that function. Yeah, but I'm saying you can construct them with this problem.
I'm not sure like what psi x is such that it makes use of this expression.
Right. So we have a vector space, which is the space of conformal blocks. Psi x is some element of that vector space. It depends on the data of G numbers, xi. And then LAI is an operator on that vector space. And so I'm saying that this psi x is an eigenvector of the operator LAI with eigenvalue xi.
And it's like honest element, not some distribution.
Honest element. They're honest functions. Again, we could maybe write them later on, the actual explicit construction of the functions. But that's right, it's an honest thing. It's not like a distribution. Yeah, even though if you thought of these as, right, if you think that you're modeling this thing as like the space of functions of x, then these would be sort of like the delta functions. But they're honest elements of this vector space. Okay, good. So these Heisenberg conformal blocks are sort of relatively concrete and accessible things. That's what I'm trying to say. You can construct them in an explicit fashion. And you can more or less understand the structure of the space of them. As a matter of fact, it is homomorphic in X. I'm not sure whether that had to be the case based on everything I've told you so far, but it is in fact true that they depend.
Complex and not real numbers. I expect the usual Schrödinger.
That's right. I mean, okay, it's just a fact that for any complex number, I can produce one of these eigenfunctions. I think it's true that, you know, when you go and you do like when you study, for example, Liouville theory, then you're going to find yourself using only the ones where this x is real. But so far, at the level of what I'm saying, so far I can take x to be complex. Yeah, if I change the A and B cycle, then it transforms in, you know, yeah, it transforms essentially by Fourier transform. Yeah, it's the usual thing for the kind of Schrödinger representation. Yeah, it's the usual thing. So like, you know, if you just change the B cycle, then you multiply it by some quadratic e to the something x squared. Yeah, it's exactly like it would be in quantum mechanics for the standard representation of the Weyl algebra. Okay, so that was conformal blocks for the Heisenberg algebra. Now let's talk about the Virasoro conformal blocks. Okay, so let's, so unlike the story I just told, this story will depend on a parameter. So from the very beginning, let's fix a complex parameter C. And now I'm going to write the relations of the Virasoro algebra. So in the same sense as I wrote before J of Z, J of P, J of Q goes like 1 over the difference of Z squared plus regular. In the same sense, let me now write the relation of the Virasoro algebra. So I'll write T of P, T of Q So now we're going to have a single field again, which is called T instead of being called J. And the rule is that when P comes close to Q, we get now a fourth order pole instead of second order, whose coefficient is half C, Z of P minus Z of Q to the fourth, plus 2 times T of QZ divided by Z of P minus Z of Q squared, plus the derivative with respect to Z of T of QZ divided by Z of P minus Z of Q plus regular. And so I'm going to consider conformal blocks where now everything is going to be written exactly like before, except that now the condition along the diagonal is going to be that the poles are of this form, so a fourth order pole plus less. And the change of coordinates law is also going to be more complicated. So to change coordinates from Z to W, now I get, so before I just got a factor of dz by dw. Now I get dz by dw squared. So if I just had this, it would be a holomorphic quadratic differential. But the bad news is that I have to write something else. Well, bad or good news. So it's not quite just a holomorphic quadratic differential. There's this correction involving the central charge and the Schwarzian derivative of the change of coordinates. So, and by definition, this, I'll just remind you what Schwarzian derivative is. So it's Z triple prime of W over Z prime of W minus 3/2 Z double prime of W divided by Z prime of W squared. This is why I'm saying it in this complicated way about dependence on coordinate systems. If not for these inhomogeneous terms, we would have just said it's a one form, and here we would just say it's a quadratic differential. But the point is, here it depends on the local coordinate in a slightly more complicated way. Okay, so those are the relations, and now, so let me write these relations star. There is some reasonable way of saying it, but it doesn't come, I can never remember exactly what the reasonable way is. And in practice, somehow this is the thing you actually wind up using. At least I actually wind up using.
You can't even remember the other one.
Well, that's true. You might not be very convinced. Yeah, but I think if it was useful, I would have remembered it. Okay, so then a Virasoro block on C, an element of, so here's the space of Virasoro blocks, is, so again, just like before, so it'll be a collection of numbers. Now I write T of P1, Z1 up to T of Pn, Zn. And I'll just say that they obey these relations. They obey these relations star in the same sense as I had before. So, okay. So by a Virasoro block, I just mean a bunch of, roughly speaking, meromorphic functions on symmetric product of the curve with some complicated dependence on the change of coordinates and some slightly complicated behavior near the back. Okay, so what can we say about the space of conformal blocks for Virasoro? Well, okay, the first thing to say is that it's harder to understand. It's harder to understand than the space of conformal blocks for the Heisenberg. On the other hand, it carries a lot of sort of interesting structures, and it's been studied from a lot of different points of view. So let me tell you some of the things that are kind of expected to be true about this space. So what are the things that people believe about this space? So first of all, so before I told you roughly that for Heisenberg, we would get some distinguished conformal blocks, roughly speaking, a basis of conformal blocks by choosing A and B cycles. Here, the parallel thing is not to choose A and B cycles, but one thing you can do is you can choose a Pantz decomposition. So a Pantz decomposition of the surface is supposed to give a, so I write basis in quotes, of the space of conformal blocks. And those bases are kind of, well, they're used in many different contexts, but one place where they're used is in the work of Aldai, Gayoto, Tachikawa. These are the ones that are supposed to be related to the Nekrasov instanton partition function in n equals 2 theories. So when people say, like, the instanton partition function has something to do with conformal blocks, what do they really mean? They mean these particular conformal blocks that have to do with a Virasoro conformal blocks that have to do with the Pantz decomposition of the surface. Okay, also expected is that if C is a surface with punctures, so I only gave the definition for surface without punctures, but there's a slight extension to a surface with punctures. And then each ideal triangulation of C is again supposed to give a basis of C.
With this punctured surface, sometimes when you discuss about the punctured surface, you get to put this kind of marked punctured surface or whatever. Is it like that? Or
Yes, yes. You put some data at the puncture. So in this case, the data would just be a.
like I know how many triangles come with a puncture.
Oh no. Well, that's determined by. No, just any ideal triangulation of the surface. I mean, if you have a surface with a given fixed number of punctures, there's some set of ideal triangulations of that surface.
And maybe that's a different question. So with this talk about people, they sometimes then put a more general than punctured surface, which is just like marked surface.
Oh yeah. I'm not talking about so that would have to do with the Virasoro blocks with so-called irregular singularity.
But that's also it.
That's also supposed to be in there, but I think those definitions, like the definition with the ordinary punctures, I can easily tell you what it is. You just require second order poles of T with some specific coefficient. For the irregular singularity, people have said things, so like there's a paper of Gayoto and Teschner, and there's various follow-ups, but I'm not sure if everyone completely agrees on the definition of conformal blocks with irregular singularity. So let me avoid that. But it is believed, and this is one of the famous things that Fak and Goncharov proposed, is that there ought to be if you have any ideal triangulation, you ought to get again a basis for the space of conformal blocks. Another thing that's supposed to be true is that the space of conformal blocks. So far I talked about it on a fixed surface. Yeah, so I'm in trouble, right? Because even in the case of Heisenberg, where I said I understood everything, I told you this big continuous collection of vectors, and I kind of said that those should be roughly speaking a basis. It's in the same sense here. So maybe the best thing I can say is that every conformal block that anyone cares about is expressed as a linear combination of these. Okay, so other structures that this space of conformal block has, so it's supposed to carry, right, so far I just talked about a single surface, and then we have the space of conformal blocks over that surface. A little more generally, you could imagine a family of surfaces. Let the complex structure of the surface vary. Then for each of them, we have the space of conformal blocks. And the space of conformal blocks, that bundle is supposed to carry a connection. Connection over mg. And I'm lying very slightly. It's a twisted connection, twisted flat connection. But for example, it would give an honest flat connection on the bundle of projective spaces. Another structure it's supposed to have. So people try to use that to make, for example, it's more than projectively flat because knowing the twisting means you kind of know the projective factor. But in particular, yeah, it's an honest projectively flat connection. Okay, and then, so one other thing I'll say is that it's supposed to form a representation of the Kaufman bracket skein algebra. And then, sorry, one more. If you choose a representation of the fundamental group, that's supposed to determine for you, well, okay, plus some additional discrete data. That's supposed to determine for you a section, tau lambda, of this bundle of conformal blocks. Well, let's just say an element tau lambda for each surface, an element tau lambda in conf C, where C equals 1. And then the 1-point function in that particular conformal block is what's known as the isomonodromy tau function. So that's, in this context, that's due to Gamanian, Yorgov, Lisovi. Okay. So all this is just to say that this space of Virasoro conformal blocks is supposed to carry kind of a lot of interesting structures and be connected to various things. On the other hand, it's not.
Can I ask about expectation?
Yeah, yeah.
So when you say these like various things give the basis, is it that they can write down some elements but they just don't know its basis?
They can write down some elements, and for example, if you so here I said each Pants decomposition gives you a basis. So there, what I mean is that they can write down a bunch of elements for each Pants decomposition, and then they can give you the kind of change of basis that expresses the ones in relative to one.
They write down the Pants, like check the fact that there are elements of this or in fact conformal blocks.
They check the fact that there are elements of this space, but they don't check that they're a basis.
I see. They show any triangulation of these factors.
I mean, okay. Sorry, let me be more precise. There is a construction, given a Pants decomposition, there is, I think now it's actually rigorous mathematics that there's an actual construction of conformal blocks. Up until very recently, there was not, because they were given by some sum expansions, and it wasn't clear that the sums were convergent. Very recently, actually, the probabilists working on Liouville theory, I think, have filled that gap. So I think they've now given an actual rigorous construction of those conformal blocks. But it certainly was not an easy thing.
Teschner's solution of Liouville theory from like way before AGT did not cover?
I don't think that he. I think he had those series expansions, but I don't think he proved that those series expansions were convergent. Yeah.
So, like approximately what is actually the definition for small blocks and not a regular singularity?
With irregular singularity? I mean.
Well, like one part of the definition you gave is somehow like regular singularity.
Well, okay. So what you would do? So what I said in the definition without the singularities, right, was I said that the correlation function is supposed to be holomorphic, right, away from colliding insertions. So when you want to insert additional singularities, then you don't say they're holomorphic anymore. You say that they should be, they should have singularities when. So suppose I have some fixed singularity here. Call it Z star, and here I insert T of Z. And now you ask what should happen as the insertion T of Z approaches Z star. And you want to impose some condition. Like for a regular singularity, you would put a condition like H divided by Z minus Z star squared plus lower order terms. That's what you would do for that's what you call a regular singularity. For irregular singularity, you want to put a higher order pole here. And the question is just what exactly what condition should you put at that higher order pole? Yeah.
So is it known that, not back about these things,
Yeah.
is it known that the Coman-Longhi-Pomoni-Teschner algebra acts on the thing spanned by basically these like elements that are known?
I think that is known. I think that you can really construct. And that's somehow the best construction. It's kind of funny, the construction of this action of the skein algebra, when you first see it, you think that it's a completely canonical definition. When you look closely, it has one ingredient which I don't know how to make sense of without referencing this specific basis. Yeah, so that construction is in the papers of, well, in the papers by two groups on line operators in AGT around like 2009.
But when you say there's a condition of the Coman brackets in algebra,
Yes.
these kind of, here you have literally Riemann module insertion, right?
Here I have nothing inserted. I'm literally just talking about a compact surface, say genus 4 or something.
Okay, but if you cut it, what propagates in every single cut, like.
So I think you're asking about writing it in this basis, at the top. Yeah, that's right. So then you would have just the most generic things flowing, any real numbers.
It's not that it's going to be Coman, I mean, it's not possible it's a Coman bracket scheme algebra because Coman bracket refers to fundamental representation as algebra. It definitely has nothing to do with the continuous level of representation that is what you're going to find in your source.
Right. Well, so we have to distinguish, I think. Certainly, in defining the action of the Kaufman bracket skein algebra, what you would do, right, is you would start with your conformal block, whatever it is. Whatever representations are flowing in whatever channels, however you want to describe it. Then you would have to insert, or you have to create from that conformal block another conformal block with two insertions, right? Those insertions certainly are insertions of the degenerate representation, not the continuous representation. Then you would take those degenerate representations, move one of them around a loop, and come back.
Yeah, in that case, yeah.
The claim is that procedure.
However, this still has to be a statement not on a genus surface, but just locally on the disk. Because if you, I mean, such a thing wouldn't be true even for SF2 hat, right? Because the stuff that's running through the Riemann surface itself in general, it's stuff. The actual loop lines that you want. So I think what you want is you want to pick a disk and say that on the disk rating might be a representation of the Coman bracket scheme algebra. That would be true. But
No.
Yeah, I think I'm saying what I mean.
Real momentum continues, right? So there's
No, that's right. But these operators act in the basis of Liouville momentum.
I know, but you can't even phrase it. The scheme algebra, the Coman bracket scheme algebra deals with how does it know what flows through what flows through the circle? Like pick some conformal block, right? Then pair create those guys.
Yeah.
You're saying that the algebra line operator is not going to know which conformal block to pick?
No, I mean, I guess I am saying that, right? It acts on that basis in a relatively simple way, right? It shifts the momentum. So if you work in the basis where this is one of your pants curves.
Like how would brackets don't know that? They don't have the data to describe it. I don't think so.
I mean, the algebra doesn't know it, but the way it acts in the representation does. Anyway, maybe I can So I think I said the correct thing, but we can argue about to what extent it's proved or not, but certainly this is what's supposed to be true. Okay. Oh, what's the Kaufman bracket scaling algebra? Yeah, it's so.
We just learned last week.
It's actually a lot like the. So it's a little bit like the thing I told you for the Heisenberg. So for every loop on the surface, there's a generator of this Kaufman bracket scaling algebra, and then they don't commute. Those are generators of some algebra. Their product is not commutative. And the product law, now I won't write it exactly right, but the product law is something like, so I'll draw it like this. So if I have two loops that don't cross, they do commute. And if I have two loops that cross, then they don't commute. And then I could represent the relation that they obey is like this. It's like, yeah, it's like, it's the sum of something like this and something like this with some coefficients depending on Q here and here. That's for sure. That's for sure. That's right. Okay, good. Okay, so I think I'll just tell you briefly about the rest of the story. So the goal, the thing I want to tell you, is to try to understand these structures in a more explicit way. To understand these structures more explicitly. Yeah.
Is this Tom C very supposed to be the Kaufman bracket scaling model of the hand body?
No, I don't think so.
What else can the Kaufman bracket scaling algebra possibly have?
I mean, it has a map from the Kaufman bracket scaling algebra of the handle body, but I don't know if it's equal to the.
It sounds like very function.
Maybe. Okay. So the goal is to give some kind of explicit way of thinking about this space of Virasoro conformal blocks and these structures on it. So the dream is to do it for every value of the central charge, but so far we do it only for central charge equals to 1. But that's already non-trivial to do it for c equals 1.
Can you say something more about that
Yeah, what about it?
energy momentum?
Yes. Yes. I mean, it is. So if you had any conformal field theory, then and you just look at the energy momentum tensor, then it obeys the relations of the Virasoro algebra. Here, I want to think of it kind of in the abstract. So I don't think of it as embedded in any particular conformal field theory. It's like we're just studying. If you like, a Virasoro conformal block is like some structure that you would get in any conformal field theory, no matter what it was. Because in different CFTs, you'll have much more structure layered on top of that. But this thing is kind of universal. Every CFT has it.
What's the meaning of this?
Well, as a practical matter, I mean, you want me to say something beyond just the stupid fact that it appears differently in the it appeared explicitly in these equations? You'll see in a second why c equals 1 is special for us.
Does specializing, I mean, this Kaufman bracket scaling algebra has some coefficients.
Yes. Oh, for c equals 1, it's commutative. Yes. So certainly that part is simpler here. Then it becomes then the spec of it is the character variety. Okay. So what's the idea?
It's supposed to be like a simple model for this Kaufman bracket scaling algebra, or it has some history?
No, I don't know. I don't know. It's just a representation. That's all I want to say, though. All right.
So the action is still like previously, especially by
The action of the skein algebra? No, the action of the skein algebra on the Virasoro blocks is a little more complicated to construct. You cannot get it just by doing the simple thing that I said. So maybe I'd be in a position. Yeah, actually, at the end of the talk, I'll be in a position to give you some construction of it. Okay. Okay, so what I want to talk about is a way to relate the two things that we discussed. So suppose I have my surface C. I want to understand the Virasoro blocks on C, and the way I'm going to understand it is to consider a double cover, a branch double cover of C. Smooth branch double cover. So maybe it looks like this. It's branched at some finite number of points. So here we have the space that we want to understand, the conformal blocks for Virasoro. And the idea is going to be to relate it to the conformal blocks here for the Heisenberg. So this is the one that I told you is easy, in the sense that I can construct a whole pile of conformal blocks here. Here, I have a real hard time making any conformal blocks. And the idea is going to be to produce a map that takes a conformal block here for Heisenberg and maps it to a conformal block here for Virasoro. That map we'll call F. Actually, to be exact, we're going to get not just Virasoro, but Virasoro times Heisenberg. So we're going to get correlation functions that can have both T and J on the base. But the Virasoro is kind of the interesting part, so I focus on that.
So is it there is a kind of Abelianization of Virasoro algebra? So you have two models, and then you do one part.
Yeah, it kind of begins with that. Yeah, so that's part of the story, but that's not the whole story. But yes, yes.
I mean, the same thing people usually do in AGT.
Let's go on and see. So for Virasoro, but it's only going to be Virasoro at C equals 1. Okay. So what's the idea? So we're going to get there in steps. So let me first make a first kind of attempt at it. So, I mean, pragmatically, what do I need to do? I need to define correlation functions down here involving insertions T of P. I need to make a correlation function down here, and I'm going to relate it to a correlation function up here. How will I do it? Well, almost the only thing I could do is everywhere I see a T of P here, I'm going to replace it with J of P1. So let's let P1 and P2 be the two preimages. I'm going to replace insertions of T here with some combination of insertions of J up here. So my dictionary will be like this. T of P will be replaced by J of P1 minus J of P2. So I take the kind of anti-invariant combination of these two, and I square it. So this is some bilinear in the J's here. Except, of course, I said that the correlation functions are only defined away from coincident points. So here I have J of P1 times J of P1. So I have to deal with that. And the way we deal with that is the standard thing, this thing called normal ordering, which amounts to saying you split the points slightly. then you write the correlation function as a function of the split points, and you just throw away the singular part. Looks like a brutal thing. It depends on the coordinate system in a nasty way. But that's actually what you want, because this T of P, as we know, depends on the coordinate system in a nasty way. Okay, to be precise, we'll put 1/4. Okay, so that would be our dictionary. And then what we would define is, so I want to define a correlation function for Virasoro in a block f of psi. So I've got my block. I've got a Heisenberg block here. I'm trying to define f of psi. So the correlation functions in the block f of psi will define to be equal to the correlation functions upstairs in the block psi, where I just apply this ab map to all the insertions. So if I have 3 t's, I'll apply this ab to it, and I'll get some combination of 6 j's up on the cover. I compute the correlation function here, and that's supposed to give me the correlation function here. That's the proposal. So for example, just to write it real concretely. So for example, the 2-point function of t of p and t of q in the block f naught of psi, by definition, is going to be 1/16 the correlation function j of p1 minus j of p2 squared times j of q1 minus j of q2 squared in the block psi. Yes? Yeah, that's right. If I did the Heisenberg part, then I would write j of p1 plus j of p2 and without the square. That's right. That part is relatively trivial, so I won't write that part. But yes, that's how it's supposed to enter. Okay, so we could try this. And let's see, does this give us a conformal block or not? It points with only one preimage. Oh, good, good, good. So you're already getting to the issue. So so far I gave you a formula which only works when the p's are away from the branch points. And now you may very reasonably ask, what happens when the p's approach the branch points? So okay, we get to that in just a sec. So in fact, we get to it right now. So f naught of psi has all the desired properties. Meaning, for instance, you can compute the singularity when 2 of these t's approach each other, as long as they're away from the branch points. And that's fine. It's exactly what it's supposed to be. That's a well-known thing. That's the usual free field construction of Virasoro, for those who know. Anyway, it's not a surprise that that works, but that works. And then the issue is, the problem. What's that? The free field, so this j of p1 minus j of p2, like you could have called that, you might have called that like j minus of p. And then what we're doing essentially is we're saying t is, j minus of p squared. That's the usual thing you would do with a free boson. Here, there's some slight subtlety, right? Because this thing is only defined up to a sign, but of course, since we're squaring it, it doesn't matter. So the fact that there's a kind of Z2 twist in our free boson locally doesn't hurt us. Absolutely. If you took the trivial double cover, then this would be literally what's usually called the free field construction. Absolutely. That's right, that's right. So it has the design properties in the sense that they're meromorphic, they have the right coordinate transformation law with c equals 1. Right, so that Schwarzschild derivative does actually come out if you carefully calculate here. If c is not equal to 1, then we cannot use this free field realization. This free field realization is specific to c equals 1. You could have done something, so I'll just say, so the free field construction for other values of c has this form. It looks like 1/2, okay, I'll just say j squared plus something proportional to the derivative of j. And the thing is that this, so this is what you would get This would give you C is 1 plus 6q squared. But the trouble is that this part is not invariant under changing j to minus j. And so when I swap the two sheets, it would screw up this term. So that's why we can only do the thing at c equals 1. Yeah, by j, exactly. I mean the j minus up there. Okay, so this thing has all the desired properties except that we get unwanted singularities at the branch points.
The reason you don't want to just use a trivial double cover is you want to get more.
That's right. So indeed, so you could say, well, what the hell? Why don't I just use a trivial double cover? Right? Why don't I just use a trivial double cover? Then I have, conformal blocks on, on this curve and on this curve, and I'll just map those to conformal blocks down here. And indeed, in that way, you can get some very special conformal blocks down here. In the usual free boson, right? You might have said, what's the big deal about Virasoro conformal blocks? Because there's free field construction of Virasoro. Why don't you just use the conformal blocks for the free boson, right? And you can, but you just don't get enough that way. That gives you just some very special conformal blocks. So the idea is we want to get in some sense the most generic conformal block. We will not get it from this surface. Its genus is too low. But if we take a branch cover, we will get enough. That's the idea.
Insofar as space of conformal blocks is modular for functions on the character graph.
Only at c equals 1 it is, but yeah.
Let's say at c equals 1. Do these free field ones, do they sit all over the character variety, or is there some kind of special part? Or?
The free field ones, yeah, the free field ones will correspond to the representations that are globally diagonalized. In other words, it'll be like if it splits as a direct sum of u1 and u1. Yeah. Right. So from that point of view, you see right away that it's missing most of what you want.
Sorry, why did you say that it's only the sequence to 1 that are, in fact, the sequence to 1 are the ones that I think you missed?
No, I'm saying that in this construction, I can only produce the conformal blocks with c equals 1.
But the ones that are related to the character are actually generic. Or generic conformal blocks.
There's various different ways that the character variety enters into this story. So here, I mean, what I think Vivek meant is that the skein algebra at c equals 1 becomes the algebra of functions on the character variety.
I see. So in general, you get a quantized.
That's right. You could say that in general, there's the quantized character variety, but here I'm talking about the classical. Right, then the skein algebra just becomes functions on the character variety. But nevertheless, it's interesting to know that the thing is a module over, that says it kind of sheafifies over the character variety. Yeah. Okay. So,
And by the way, what if you took not the trivial double cover, but a nevertheless unbranched double cover, which is not topologically trivial?
yeah, I don't know. So we haven't very systematically studied what you get with all kinds of covers. So, I mean, we have some class of covers where we expect to get, in some sense, all the conformal blocks, namely the ones that come from holomorphic quadratic differentials. Of course, there's tons of other covers that you can take. Yeah, so I don't know how to identify the subset that comes from each possible cover.
So do you think you'll eventually have something that works with generic?
I very much hope so. Yeah, there's many reasons to think that we should. But there's at least one key ingredient missing. Okay, so if you want me to bet, I bet yes, we will. But I can't, I could say anything, right? Yeah.
So you said you just take the trivial number, you don't get enough conformal blocks?
Right. Well, for example, you don't get enough. Suppose I want to reproduce all those bases that I was telling you about. You certainly won't get enough to produce the guys that are in those, that make up those bases. I mean, informally, there's a kind of functional dimension here that you count. So, and the functional dimension that you want for a genus G surface, you want to get 4G minus 3. That's the amount of kind of continuous parameters that you expect to have. And so, to the extent that your double cover has genus less than 4G minus 3, you're not going to get all of them, right? Because upstairs, my conformal dimension was just the genus of the surface. So what you want, ideally, is a covering whose genus is 4G minus 3. There's a natural source of such coverings, which is holomorphic quadratic differentials. But if you take a trivial double cover, it kind of has genus 2G, and that's not good enough.
So were you talking about four of these bases that correspond like
yeah.
So that was just for Virasoro, not
That's for Virasoro. That's right. That's right. That's for Virasoro.
So what's the relation between like what happens when I observe the I?
Well, the Heisenberg just adds on top of it a separate thing, which depends on a choice of A and B cycles on the base. Yeah, that part is relatively more. Okay. Okay, so I'm describing this construction where we take a branch covering and we just push down the conformal blocks, and it almost works, but there's a problem. The problem is that you get unwanted singularities at the branch points. So, yeah.
So you see the normal algorithm is to get rid of this self-product.
That's right, that's right.
It's like the same as JP1 plus JP2.
It's a little bit tricky. It's not exactly the same as the normal ordered product. Take the normal ordered product of two things is not the same as just eliminating the thing. You have to keep the constant part. So it removes the singularity, but it doesn't completely remove the. Okay, so at the branch points of this covering, there my prescription kind of breaks down, right? Because I told you what to do for points. I told you what to do for insertions of T at generic points. I didn't tell you what to do at branch points. Well, pragmatically, you could just ask, okay, maybe you just continue it by like removable singularities theorem. So the real question is there a singularity or not as P approaches the branch point? And the answer is that there is a singularity, unfortunately. So what you get is something like this. You get that the correlation functions behave like 1/16 divided by z minus z of the branch point squared. So if I call this branch point z star. You get this bad singularity with coefficient 1/16. Okay, so that's actually been well known for a long time. So if for some reason you wanted to compute correlation functions with that specific singularity, this construction would be perfect for that purpose, right? It says you would use some particular correlation functions downstairs are given by just essentially theta functions, because they're just given by Heisenberg blocks on this double cover. And that was used by Zamolodchikov. Apparently, the C equals 1 CFT with insertions of conformal weight 1/16 is called the Ashkin-Teller model. And so there's a paper by Zamolodchikov where he explains how to compute correlation functions in the Ashkin-Teller model in this way. Sometimes people call these, another buzzword is people call these twist fields. So this is like you're computing correlation functions with some twist fields inserted.
There's also some old papers by like Neitzke on the same thing.
Oh, really? Oh, okay. Oh, good.
It's like analytic fields on Riemann surface.
I see. But the same idea of computing.
Yeah, it's like basically like if you want conformal blocks on some higher genus thing, you realize that it's ranked by covering, and you can put some kind of money insertion in the branch point.
Right. Anyway, so that's a known and kind of interesting thing, but it's not our purpose. Our purpose is to compute correlation functions without this singularity. Okay, so now I come to kind of the only real innovation that I'm trying to tell you about. So how do we remove this singularity? How do we kill this singularity? Right, so F0, by definition, F0, oh, sorry, here I wrote the 0, but I forgot to write it up there. So F0 was the map that was literally defined by this rule. So the correlation functions in the block F0 of psi, I get them by taking all my insertions, lifting them up to the cover, and just doing this. That's F0. Okay. So now, how do we remove this singularity? Well, there's no completely canonical way to do it. We have to choose some extra discrete data. But just discrete data. And this extra data is, because it arose in other contexts where it was called a spectral network, but pragmatically what it is at each branch point, so for each branch point of the covering, I'm going to draw 3 lines, which I call walls, emanating from that point. And for a while, don't ask me where the other end of them is. If we have punctures, then you might imagine that these things end at the punctures. Otherwise, just imagine they run around the surface forever. So we're going to insert these three walls on the cover. And so these three walls on the base. On the double cover, since this is a branch point, the mapping is ramified 2 to 1 around this point. And so each of these three lines will lift to actually a pair of lines on the cover. And I'll decorate them like this, alternatingly dashed and solid. And so given a point here on this wall, it's going to have its two preimages, P1 and P2. In this picture, they're sitting kind of, at opposite ends of the branch point like this. So I'll call this spectral network W. And now what we do is we consider the correlation functions with one additional operator inserted. So let's define an operator. I write it. Sorry, we're gonna build the operator out of free fermions. So I first have to say a word about free fermions. So in the Heisenberg block, what I said up till now is that in a Heisenberg block, you just get to compute correlation functions involving this insertion J. But in addition, you can also define something a little more general. You can define insertions where you insert these other symbols. I'll call them psi plus and psi minus. Psi plus is AR, psi minus of S. So I'm given a conformal block, a Heisenberg block. And in the Heisenberg block, we can define, in addition to the correlation functions of J, it turns out you can also define correlation functions of these objects called free fermions. That's called fermionization. And they obey the local condition psi plus of R, psi minus of S goes like just 1 over, just a first order pole, 1 over Z of R minus Z of S. It turns out there's a canonical way. Someone gives you any Heisenberg block. Oh yeah, I didn't tell you I should also tell you the OPE of J with psi. J of P psi plus minus of Q goes like plus or minus psi plus or minus of Q divided by C of P minus C of Q. So also a first order pole. So given a Heisenberg block, you can compute the correlation functions of J, but you can also compute correlation functions of these fermions. They're multi-valued functions of the positions of the fermions. That's relatively a detail. And now using these free fermions, I'll build some operators which are going to kill the singularity of our push forward. What's that? Multi-valued on C tilde. So the idea is, yeah. So for this, it wasn't important that it was a double cover. This is just a thing you can do on any surface. You have the Heisenberg blocks. You can define free fermion correlators, but generally they're multi-valued in the sense that when the fermion goes around a loop, it doesn't come back exactly to itself. So that's why I don't say that these are fields of our vertex algebra. If I did that, then I would be saying the correlation functions are always single valued. But I'm saying there's some way of extending the correlation functions to include these fermions at the cost that they're multi-valued. Okay, and then, so now I can tell you kind of the last thing. So new operator, which we attach to the spectral network. And what it is so it'll be given as the exponential of something. And now here, I write the integral over all the lines of the spectral network. So an integral over these three lines. I write a kind of bilocal insertion. I write d z of p. I insert the psi plus field at the point z1 of p. Sorry, z of p1. P1, yeah, just p1. And I insert the psi minus field at the point p2. And if I want to be really careful, I use a local coordinate which is inherited from the base in both cases. So I have a local coordinate z on the base, and I lift that up to give me local coordinate systems on the cover. And then I insert this psi plus field and psi minus field on the two preimages. Okay. And now, so now I can define my map F. W, yeah, you missed it. So we introduced this extra discrete data of a spectral network, which I call W. And so in this case, W is literally the union of these three contours emanating from the branch point. It's three, and each one of them lifts to a picture like this. We have P1 and P2. And so what we're doing is we're integrating the psi plus fermion along this line and the psi minus fermion along this line. So it's a kind of, it's the non-local thing from the point of view of the cover. So we insert this operator. And so what I mean now is that all of them. So W is the union of all of them. And so it's an integral over all the contours. If you like, it's like you're inserting. It's not quite, but it's almost like you're inserting like screening contours. You know those screening contours that people use in their free field. So these are like the kind of branched version of those screening contours. The only novelty is that we use them on this branched cover, and we make them end at the branch point.
Why are there three?
Why are there three?
Why three there?
Yeah. Okay. What would have led us to write?
What was supposed to branch points come together? Or we have that,
Oh, if two branch points come together, yeah. So we don't discuss. Yeah, we don't discuss. Yeah.
Anyway, why three?
Okay. The technical answer will be that with exactly this operator, we're going to cancel that singularity. But you want the conceptual answer. So the conceptual answer is that the problem we're dealing with is this singularity. But another manifestation of the same problem is the following. You could study the connection on degenerate field conformal blocks. So suppose I insert a degenerate field at say this point. There's supposed to be as you know, there's a connection that tells you the space of conformal blocks with this field inserted. You can parallel transport, and in particular, you can parallel transport it around the singularity. If you do that using this kind of free field construction, what the free field representation will tell you is roughly that you should map that conformal block to like a fermion on one or the other of the sheets. Then there's an obvious problem, which is when you go around the loop, it's going to come back to the other sheet. That means the connection on conformal blocks would have a monodromy around this point. It's not supposed to have a monodromy around that point, because that's supposed to be just an ordinary point. So you need some construction which would eliminate that monodromy. But as it happens, we already know a kind of a construction which does that, which you have a connection, you have a C-star connection on a cover, and you're trying to make an SL2 connection downstairs by pushing forward. You know that push forward will have monodromy, but then you also know there's this machine for removing the monodromy, which consists of inserting unipotent matrices. And then you know that you need to insert 3 unipotent matrices, because that's how it shows up naturally in WKB and so on. So we're kind of plugging into some older thing here.
And if I imagine that Marino is a neighboring branch, so that it has a net.
Yes. Yes. So then you can have something like this, Or the very interesting thing, of course, is they ask what happens when you do this. So then the construction is a little bit singular because we'll have these.
What is this geometrically? The one case or the other?
You mean?
I think of my cover. What are they doing?
I mean, as far as the cover, you can just, for everything I've said so far, these things are just topological. I mean, the only thing that matters is that they come out at 120 degrees from the branch point. There, it's conformal, but everywhere away from that, they're just topological. And so it's kind of a floppy thing. You can just draw them one way or another. It's true that if you, for some application to like WKB, then you would want to use the trajectories of a quadratic differential, and then there's some geometry, the geometry of the quadratic differential. Then this situation would correspond to like, oh, maybe this is the answer you want. Would correspond to having a little. You're going to get almost the same conformal block, but the normalization is going to be different. So there's this, there's some diagram where you take the conf on the cover. You have two different maps corresponding to the two different spectral networks. And there's some map from conformal blocks to conformal blocks that kind of intertwines with these. That map is roughly given by like the logarithm function. So there's some precise way of trying to relate these, the maps that come from different choices of this spectral network. But maybe I should, let me just, so I'm getting ahead of myself. So I told you this operator, but now just to finish the statement. So now we're going to give a map, FW, from conformal blocks, C twiddle, to conformal blocks on C. And it'll be given almost like F0 was. So just like before, I want to say what's the correlation function in my block downstairs. So before I said you just apply this abelianization, meaning you take every t and you lift it up to a product of j's. Now we still do that, but in addition to that, we insert this extra operator on the cover. And now the claim is that once you do that, first of all, it does not create any new singularities anywhere else. That you can check. You just have to check how t behaves when it comes close to one of these contours. It turns out it doesn't create a singularity. And then the kind of non-trivial thing is that it does in fact eliminate those h equals 1/16 that you had before. So once you do this, the correlation functions actually have all the properties they're supposed to have. And so that's our kind of factory for producing Virasoro conformal blocks.
I didn't quite understand. So what's the relation of the block construction and this? You think that the thing up there is not going to give you the conformal blocks you want?
Right. So the construction.
Wait,
Right. So I first made the construction F naught, and what F naught produces for you is it produces conformal blocks with twist fields. So it's perfectly good if you wanted twist fields. What's wrong with a twist field? Well, nothing, but I wanted to construct the conformal blocks without a twist field.
Why is it better without a twist field?
Why is the space of conformal blocks?
You say conformal blocks or what's that?
I think he's kind of after like more general conformal blocks of Virasoro on the.
Right, I'm trying to construct all the, in some sense, which I admittedly cannot make precise, but clearly in my head, what I want is all the conformal blocks of Virasoro.
And you're saying the twist fields will give you just a subset?
Well,
conformal blocks of Virasoro at all.
right, they're conformal blocks with extra insertions that I don't want. So that's some different kind of, different category of object, yeah. It also doesn't give you all the conformal blocks with twist fields, by the way. If it did, that would be a little interesting.
How do you show that they're not Virasoro conformal blocks? What's the
Well, they are Virasoro conformal blocks, but with an additional primary is inserted at the branch points. So they absolutely are Virasoro conformal blocks.
I mean, in the end, the thing is a function. You get a function you want.
Absolutely, you get a function.
You want or you don't.
Right. The only problem, yeah, you get functions, but they have this extra singularity. They have a singularity at the branch point, and I do not want that extra singularity. And the claim is that it can be eliminated by adding this additional ingredient.
So is this are you?
That's a good moment to stop. Yeah.
So
No, 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 no. I'll say a little more.
In your old works, this spectral networks, one point of view on them was that they were some kind of code for holomorphic disks and some cotangent bundle or something.
Right.
Is this term the area? Some integral over that holomorphic disk?
It should have some interpretation like that.
I mean, this looks like the value of like d of some function you integrate over the disk.
I mean, this you integrated. One thing to say is you integrate over the whole wall.
Yeah, but that's the boundary of the disk.
I think usually the interpretation of those disks, if I remember right, was you pick a fiber of the cotangent bundle. You pick your favorite point which lies along the wall, and then the observation was that there exists a kind of bygone or whatever you call it.
I mean, that's true, but you could also just say, I take my spectral curve.
Let it go all the way to infinity.
And I just ask, like, what are the holomorphic disks depend on this curve?
Well, right, but that's these. That's not. That's this one.
I mean, but it's an unbounded one. Like it's a.
Oh, you want that? I wouldn't.
Well, but that's what the integral is. It's like a.
It is, but morally, okay. I could be wrong, but I would be surprised if that's the interpretation. Okay. Anyway, so this is the proposed construction, and so the idea is first the first zero order thing.
Let me press on it. So you can imagine you had some construction setting constraint here.
Yes.
And then how would this construction work? It would have to be like looks like a stupid Abelianization plus some corrections and like some grains. The only grains inside it are these things.
I agree. I mean, I agree that it's somehow that that object.
Must be,
I just don't want to think of this as being the area of the disk. I think
what else could
it comes from that disk, but
maybe not area, maybe something else. But,
yeah. I mean, first of all, this is not a number. This is some operator that we're building on the right. I mean, this psi plus and psi minus are going to be operators that get inserted into the Heisenberg conformal block. Oh yeah, maybe you missed that part. So this psi plus and psi minus are some complicated additional insertions that you can make whenever you have a Heisenberg block.
But actually, geometrically, right, you know the translation between size and the grain. So what actually, what does that look like, this particular operator? I don't remember. Wait, can you draw it over there on the
This operator, I mean,
right-hand corner? Oh yeah, over there, right, that's picture.
yeah, I'm putting psi plus here and psi minus here.
And so they're basically two halves of a grain that meet like this? They inserted, yeah, and what Jeff was saying.
I'm actually, yeah, I mean, for a little while, I haven't been thinking of it in terms of brains so much. I've been thinking of this just as a CFT thing. I mean, yes, so you put the two fermions at these 2 points.
Right, I mean, they must be pointing this way as the central part of the brain. Kind of an operator alternative.
Certainly, it is some integral over the boundary of this disk. I agree with that.
Is there some special properties of OW, like if I have this line so that I have something like J or T passing through one of the lines?
Yes.
There's some commutation problem, so
Yeah, so the point is they're transparent. Yeah, it's just like the screening charges in. They're transparent on the base. They're transparent for T and J on the base, not for J on the cover. Yeah, for J on the. For J on the cover, there's some discontinuity when you go across the. Yeah, I haven't made as much use of that maybe as I should. Right. Yeah.
Sorry, just like a
Yeah.
Are you saying like full multiple C cells with Heisenberg with like module insertions at these points where the module depends on W equals full?
No. With no module insertions.
Okay.
I would say conformal blocks with no module insertions. Right. So that was why I emphasized that given a conformal block for Heisenberg, there's a canonical way of defining the free fermion insertions. So I I agree that one way of thinking of it would be that you have some module that you're inserting and you travel along. But you're not obliged to think of it that way. You can just think that this is some gadget which you could compute completely using the data of the original conformal block. Yeah.
What are these two fermions?
Yeah, okay, so maybe I should just give you a formula for it. So what I said is that if you have a conformal block for Heisenberg, then there's something called fermionization, which is a way of constructing some additional insertions. It's some complicated composite built out of J's. And if you want, I'll write the actual formula. But
you told us what kind of thing J was. J was like a...
That's right, that's right.
What kind of thing is this?
Right, right. So this psi plus and psi minus are, so first of all, they obey this kind of operator products. And as far as the change of coordinates, they transform like sections of k to the 1/2. I mean, you're using both, right? I mean, this part is the structure of module over Heisenberg. But then, in order to actually define these correlation functions, you have to use a little bit more because we need to have a family of those conformal blocks with the module inserted, depending on this parameter. So what you use is the connection, right? You know that whenever you have a conformal blocks with modules inserted, there's a connection. Here what we're considering is a flat section of that connection. Flat is a function of R and S. And that determines it up to a scale, but you need to somehow fix the scale. The way you fix the scale is to specify what happens when R and S come close together, and that's where we use this. It's not an extent. We're not taking an extension of the Heisenberg vertex algebra because if we did that, that would conformal blocks with that extension would have the additional property that they're single valued as functions of R and S. That's what I do not want to do. So I'm not saying, I want to emphasize this. I'm not talking about conformal blocks for the free fermion vertex algebra, which would be some finite dimensional. That's a very special example of this.
So sorry, can you say that psi plus and psi minus are like exponents of the integral?
Yes, yes. So you could write psi plus, let's write what psi, let's write, it's actually the composite that you can write. So I can write psi plus of R, psi minus of S equals 1 over z of R minus z of S times the normal ordered exponential of the integral from R to S of J. That's the formula which defines for you the insertions of psi plus and psi. Yeah, maybe that's the better way. Okay, so we said a lot of stuff about modules and all that stuff was true, but maybe it's better just to say this. It's better just to say here is the formula. It's multi-valued because it depends on the contour of integration from R to S.
The psi plus itself is not a multi-valued.
Psi plus itself is just some symbol that I write here, but
no, but you also told me what kind of thing it was. It was a section of.
It's a section of k to the, it has locally the transformation. I mean, these correlation functions depend on coordinates in the way that a section of k to the 1/2 would depend. But they're multi-valued in the sense that if I go around a loop, I don't claim that it comes back to the same section.
So you refuse to tell me where psi plus lives. It's not like an element. You told me where J was a function.
Right. And this is, if you like, a section of k to the 1/2 which lives on the universal cover of the surface. A section of the pullback of k to the 1/2 to the universal cover of the surface.
Does that satisfy no transformation law? Or?
No, it satisfies a differential equation.
For example, if I go around the loop twice, like when I go around the loop, I can come back to anything?
Yeah, you can come back to anything because you get there's a connection which tells you how it depends on the insertion. One way of expressing that dependence is just to write this formula.
And for the generic central charge, there's an obvious deformation of this formula, which you don't think is the right one. Why?
This part of the story, I think we could deform to other central charges.
I think it should be right. Why should it not be right?
Yeah, the part that I don't know how to do for general central charges is actually the part earlier. I don't know how to make a branched version of the free field construction. I mean, I'll tell you what's missing, by the way, because maybe you know actually what the correct thing is. You probably know very well that that in Liouville theory, there's this reflection symmetry that relates kind of the insertion, the free field insertion alpha and the free field insertion Q minus alpha. But that symmetry is implemented in a slightly non-trivial way. There's this thing called the Maulico-Klunkov R matrix that somehow tells you how that symmetry is implemented. And morally, I would be very happy if so you can think of the Mollico-Kunkov R matrix, I think, as even an operator that acts in a single representation after you make kind of the proper conjugations. You can think of it as an operator that acts on a single representation. And I would be very happy if that was realized as the contour integral of some kind of current. If I knew that, then I could use that current, put it on the branch cuts of this covering, and I would kind of be in business.
So more the sticky, like this whole W is some remnant of this R matrix, or something like leading to it.
I would say, I could be wrong, but I would say the meaning of this OW is different. OW has to do with, as I say, the lines of this spectral network. This R matrix morally deserves to go at the branch cuts of some trivialization of the double covering. It's true that you could choose to put those branch cuts exactly on these lines. So maybe in the end you're right, actually. And,
Just resembles something like that. There's an polar though, something plus times something minus.
so this I would like to understand better, actually. So I think I only know the name of the Mollico-Kunkov R matrix. Anyway, that's some future thing from my point of view. So that's why I'm saying there's one extra ingredient that's needed, which I have not used yet. Okay.
Maybe one last question. How do you actually work with exponential integers?
Right. So what this literally means is I take the sum over n of 1 over n factorial times this thing to the power n. So meaning I insert n copies of this operator. And luckily, there's no singularities to worry about with that because here on one contour, we always insert psi plus. And psi plus has no singularity. There's no singularity when two psi pluses come together. The only singularity is when psi plus and psi minus come together. In this picture, that only happens near the branch point. And so, of course, there is this delicate thing of analyzing exactly what happens near the branch point.
We're saying that you first have to have action of this SL2 of this function architecture.
Yes.
In general, scaling are not functions.
Yes.
But on the other, but at C equals 1, that's commuted with that.
Yes.
But upstairs, you still have some thing with the Heisenberg algebra, non.
That's right.
So what is?
Oh yeah. Right. Where's the abelian version of that? Right. Where's the abelian skein algebra? The answer is it's the exponential of those operators. So I wrote the relation. So I wrote kind of the Weyl algebra, right? L gamma, L mu is minus 2 pi I gamma mu. But because of this 2 pi I, if I consider the exponential of the operator, then those commute. And this is kind of the abelian version of what's called, these operators sometimes are called the Verlinde operators. So these are the abelian Verlinde operators. And those are the ones that give you the kind of, that's the Heisenberg analog of this commutative algebra, skein algebra downstairs.
But in particular, so, I mean, maybe you want to explain that. So I imagine, this kind of, this informal block, it's a module for the functions on the
Character variety. Yeah.
Let me do this sheet.
Yeah.
Now I'm pulling out that sheet by your spectral network construction, I was with the cluster chart.
Yes.
I pull back that sheet to this cluster.
Yes.
And presumably, section of the sheet pulls back to section of the
Yes.
sheet, which
Yes.
presumably matches on your expression.
Yes.
Okay. So now, but usually in this, I thought the kind of operators downstairs get pulled back to some operators. I mean, these operators pull back to operators downstairs.
These operators.
Yeah, these ones, yeah. So
yeah.
What I was going to say is, if you wanted some C not equals 1 version, then you would need the operators downstairs to get pulled back to some non-commutative operators.
Yeah, but I know what those are. So exponential of, right, so then there's q to the, if q is, e to the pi I b squared, then here there would be a q to the, So that one thing I do know, And
the last question I was going to ask you along these lines is, what sheet is it?
It's a line bundle, and it's a line bundle which people have thought about a lot. It's like the it's the line bundle that complex group Chern-Simons theory would associate to the character variety. It's the pullback from Bunge of like the standard, yeah.
So this belief about conformal blocks or whatever, a more precise version of this belief is that there's sections of this line bundle.
Yeah, I mean certainly if we look at right, so we can always kind of sheafify things relative to this algebra, and then you get down to finite dimensional things where it's just you're mapping one-dimensional space to a one-dimensional space. Then you have no problem. I only get in trouble when I try to talk kind of vaguely about the whole space. But if you restrict yourself to just the thinking about this sheaf, yeah, then everything's.
Are you saying it's known that all conformal blocks equals one intersection?
No, I'm not saying that that's known, but I'm saying if you in advance decided that what you're interested in is this sheaf, right? I mean, you certainly could define that sheaf. You could say, well, I don't care about anything else. I just care about the eigenlines of, and I think somehow that's the correct thing to do, but I don't know how to. Okay. I think okay. Now I've told you kind of the main thing that I wanted to tell you. So the further claim is just that using this construction, you reproduce various things that I said earlier. So maybe I'll just give one kind of indication of that. So